This video is going to be looking at potential energy diagrams. Before we get started on learning a little bit about potential energy diagrams, there's a couple key terms that we need to know. The first one is this idea of activation energy. And if you've already watched the video on collision theory, you probably know a little bit about activation energy. Activation energy is potential energy barrier that prevents a reaction from occurring. The higher the activation energy, the lower the reaction rate. That should be a reaction rate. The lower the activation energy, the faster the reaction rate will be. Think the energy that molecules must collide with. So again, we talked about this when we talked about collision theory. Our transition state is this unstable compound between reactants and products. I like to think of this as an orientation that molecules must collide in. So remember that there's that certain orientation. You could think of that orientation which they collide can kind of be like a transition state. A catalyst is a substance that helps to speed up a reaction. It does not get used up, that's really important, and it allows a reaction to occur at a lower activation energy. So it does not change the reaction. It doesn't change what is being produced, and it does not get used up. So when you start with a catalyst, say that a common catalyst might be platinum. When you start with something like platinum, you will still get platinum in the end. So it gets produced again. It just allows a reaction to occur with a lower activation energy. On the other hand, opposite of that is this idea of an inhibitor, and that's a substance that slows down the reaction by increasing the activation energy. So think of these two things as opposites. Now here are some potential energy diagrams. I'm going to be going through these and kind of explaining some of the different parts. So first of all, let's go ahead and look at our coordinates. So here we have energy, the amount of energy that our reactants or products have, and this is called our reaction coordinate. You can also think of this as time. So over time, how the reaction goes, how it proceeds in the forward direction. So let's say that we have some reactants that have a certain amount of energy. So not super high, not super low. And in order for this reaction to occur, it needs to overcome this kind of hump, this hill. And that distance between here and the top, that's our activation energy. Because remember, we're measuring energy right here. So this is our activation energy. At the very top of this is our transition state. So that's that kind of intermediate configuration of the molecules. Once that transition state happens, the reaction then starts to form products. Notice that our products are lower in energy, which means that an excess amount of energy is going to be released. Notice that my delta H, which we've actually already talked about this before, is our difference between products and reactants. So notice if my products are lower in energy than my reactants, here's my delta H. This is going to be negative because energy is going to be released, which means that this is an exothermic reaction. Let's compare it to this one right here. Here I have my reactants, which are low in energy. Notice that my activation energy is a lot higher. So I have this large difference between the energy that it has to overcome. My transition state up here. And then they start to form my products, and the products are, kind of higher in energy. And that difference, that delta H, is going to be positive because notice that we're not going to get all the energy back that we put in. So we have to actually put in more energy than what we get back. So this is an endothermic reaction. So what we're going to do is we are going to do this example, and we are going to draw one of these activation energy graphs or potential energy diagrams, excuse me, with this information here. So we're given that our heat of formation for nitrogen dioxide is 30 kilojoules per mole. We're given our heat of formation for dinitrogen oxide is plus 10 kilojoules per mole. We're given our activation energy is 40 kilojoules per mole. So what we're going to do is we're going to sketch that potential energy diagram for the reaction. We're going to find the values of our delta H of reaction and our delta H of TS, which is our transition state. So what energy level does that occur? we're going to sketch and find the values of our delta H of reaction and our activation energy if the reaction was reversed. And then we're going to sketch the PE graph for if a catalyst was added and it lowered the activation energy by 13 kilojoules. So we're going to put all this together and we're going to solve a problem in the next page.
All right, so here's the example that we're going to be looking at. And I've already started to sketch my potential energy diagram. So I have my reaction pathway or time. You can label it several different ways, but the most important part is that we have our energy here. So what I'm going to do is I'm going to start labeling some of the things. So we know that we have nitrogen dioxide turning into dinitrogen tetraoxide. So the first thing that I want to point out is that my delta H of formation of nitrogen dioxide is 30 kilojoules per mole. But notice that there's 2 moles of this. So really, when I put this on my graph, it's going to be 60 kilojoules. This is not per mole. This is just in kilojoules. So if I have, let's say, 10, 20, 30, 40, 50, let's say 60, 70, 80, 90, 100. So let's say right here. So I'm going to put NO2 at my 60 kilojoules. And I do know that my delta H of formation for my dinitrogen tetraoxide is 10 kilojoules. So that's going to be way down here. And this is going to be over here. So here's my reactant. So right down there, 10 kilojoules. I'm going to label this as 10 so we know exactly what I'm talking about. This is going to be N2O4. Now I can't quite draw my graph yet. The other thing that I need to know is that my activation energy is 40 kilojoules per mole. So what that means is from here all the way up to my transition state is going to be 40 more kilojoules. So this needs to be 60, 70, 80, 90, 100. Right there is going to be the top of my peak. So I'm going to kind of draw a line right there. So if I were to draw my shape, it might look something like this. So let's say that that's my graph. I'm going to go ahead and label a couple things. I'm going to label my, right here, my activation energy, E sub A for activation energy. And I also want to find my delta H of reaction. So my delta H of reaction is the difference between here and here. So here's my delta H of reaction. And this is exothermic, so my delta H is going to be negative. So I'm going to say that my delta H of reaction is 60 minus 10, or 10 minus 60, which is going to be negative 50 kilojoules. So that's my delta H of my reaction. And it's actually kilojoules per mole for 1 mole of my reaction. And then my transition state, my delta H of my transition state, well, we kind of already labeled this. My delta H TS transition state is 100 kilojoules per mole of reaction. So that is everything that we have there. So we sketched the PE graph, we found the values of the delta H of reaction and the transition state. Now we want to find the values of the delta H of reaction and the activation energy for the reverse. Now I'm not going to redraw my graph, but hopefully you understand that what would really just change for my reverse reaction, which I'm going to do everything in my reverse reaction in purple so we can kind of see the difference, is that it would be going this way. So we would be going this way towards now these being my products. So now my activation energy is the difference between here and here. So my E sub A for the reverse, I'm going to put E sub A, I'm going to put REV, is going to be now 90 kilojoules per mole. And my delta H of reaction actually is the same, but my delta H for reaction of the reverse is now a positive 50 kilojoules per mole. So again, we're going in the reverse reaction. So my activation energy got larger, and now this is an endothermic reaction instead of the exothermic, but notice that my delta H is the same. The last thing we want to do is we want to sketch the potential energy graph if a catalyst was added and it lowered the activation energy by 13 kilojoules. So if it lowered the activation energy by 13 kilojoules, that means that instead of, let's see, we had 40, so minus 13, that would be 27. So that would be 87. So let's say 87. That means that my activation energy would now be here. So if I were to draw that, I'm going to draw this with kind of a dotted slash. This would now be my graph. Notice that it does not change the starting or ending energies. It just changes how much energy we have to, how much energy has to be input. So this is my new activation energy, and sometimes we label it CAT for catalyst. So that is kind of labeling some of the graphs. Again, know where your activation energy is, where your transition state is, your delta H of reactions, your rate of formations for your different things. And then also note that if the reaction is reversed, we now have a higher activation energy for this example, and the delta H of reaction stays the same. It's just now that it's positive.
Now, there's a couple things that can happen. So let's look at kinetic energy graphs. So temperature, which we've actually talked a lot about before, measures what's called the average kinetic energy. The threshold energy is the amount of energy needed for an effective collision. So kind of think again, similar to the idea of activation energy. So let's look at the effective changing temperatures. So what we're going to do is, if you pay attention to the solid line, what we have is we have the number of collisions and we have kinetic energy. This right here, this solid line is my threshold. So what we have right here, we have just kind of like, say this happens at room temperature. Notice that the number of collisions that are effective are pretty low. So we have a low amount of collisions that will collide with enough energy. Notice that when we increase the temperature, notice that the height kind of goes down, but notice that it shifts a little bit more towards the threshold energy. So notice that the number of collisions that are successful have increased. Now, if we do the opposite and we think of decreasing the temperature, notice that by decreasing the temperature, notice the number of collisions that aren't successful. So we have the number of collisions. Notice that my peak gets higher and kind of squishes. So increasing the temperature, it kind of spreads out. Decreasing the temperature, it kind of squishes. Now we have the effect of adding a catalyst or an inhibitor. Notice that the shape of the graph does not change at all. When we add a catalyst or an inhibitor, what it does is that it changes the threshold energy and it lowers that. So we're lowering the bar of a successful collision. So notice that this solid bar right here is without a catalyst. If we were to add a catalyst, we're going to lower the activation energy, which means that we're going to have more successful collisions that are going to produce products. If we were to add an inhibitor, we would then move it this way and notice that we would decrease the amount of successful collisions. And if we decrease that amount, the reaction is going to get slower. So notice that we don't change at all this graph. We just change where the threshold energy is. So depending on where that threshold energy is, we're either going to have more successful collisions or fewer, which will then change the rate of the reaction.